Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you need any help with homework or with tutoring, then check out the links in the description below. So now let's just get started on our set of questions for today's session. Okay, so question 1. Salt dissolves in water. Is this a chemical or physical change? Okay, so let's write the definition of a chemical change. Okay, so this is when the product that is formed is chemically different from the reactant. So in the case of sodium chloride, which is salt, we start off with NaCl solid, and then when it is dissolved in water, the salt separates into its ions. So it doesn't retain its solid structure. When it separates into its ions, it becomes sodium plus chlorine minus. Okay, so you can see that comparing to the product, the sodium and the chlorine were bonded together to form like a solid, but once it is dissolved in water, because it separates into its ions, the product is chemically different from the reactant, so therefore this is a chemical change. And we can show the opposite of a chemical change, which is a physical change. So this is when there is no chemical change for the reactant. So an example of this is, let's say we had liquid water and we just heated it up and we get H2O gas. This is just a phase change, but chemically it is still H2O. And then if it were to have cooled down, it would just convert back to the liquid. So physical changes, so this is an example of a physical change when it's just a phase change of a compound. Okay, so let's see what the junior tutor said. Dissolving sodium chloride in water will result in the dissociation of sodium ions and chloride ions in water. By definition, a chemical change is the transformation of one substance into one or more different substances. Therefore, dissolving salt in water is a chemical change because the product is different from the original substance. This is true for all ionic compounds. However, for covalent compounds, such as sugar, the molecules are only dispersed throughout the water, which does not change their chemical identity. Okay, so this solution is correct. Okay, so on to question number 2, which simply just asks what elements are liquid at room temperature. So there aren't a lot of elements that are liquid at room temperature. There are only two. So room temperature, like around 298 Kelvin or 25 degrees. But at room temperature, bromine and mercury are liquids. So I think the melting point of bromine is around like 266 Kelvin. And in the case of mercury, its melting point is around 234 Kelvin. Okay, so the junior tutor said room temperature is around 20 degrees to 25 degrees, or 293 Kelvin to 298 Kelvin. Under ordinary pressure, there are only two elements that are in liquid form at room temperature, which are bromine and mercury. Bromine has a melting point of 265.9 Kelvin, while mercury has a melting point of 234.2 Kelvin. Some elements become liquid when slightly higher than room temperature, namely francium, cesium, gallium, and rubidium. They have a melting point higher than 300 K. Yep, so this solution is correct. Solution. Okay, so question number 3. What are metabolic reactions? Okay, so metabolic reactions can be broken down. They can be described into two different reactions. The first is catabolic. So catabolic reactions, this is the breakdown of food to obtain energy. Okay, so catabolic reactions are one of the examples of a metabolic reaction, and the second example is an anabolic reaction. So this is kind of like the opposite of catabolic reactions. Anabolic uses energy produced to synthesize larger molecules from smaller ones. So the two kind of go hand in hand, and we require metabolic reactions just so that our body can function. So an example of anabolic reactions, this is when you can have amino acids forming proteins. Okay, so these are the two examples of metabolic reactions. So that's why when someone says, oh, you athletes have a high metabolism, that means they can break down the food fast to obtain energy, and they can also synthesize more proteins faster as well. So the junior tutor said, metabolic reactions or metabolism is the sum of all chemical reactions happening in the living organism's body. It is either a catabolic reaction, catabolism, or an anabolic reaction, anabolism. And catabolism is the destructive reaction in the body. That is, it breaks down the food that we eat to produce energy. On the other hand, I don't even know if I'm pronouncing it right. Anabolism is the building up reaction in the body. In this process, the body uses up energy to synthesize larger molecules from smaller ones. Yep. So this solution is correct. Okay, so question number 4. A copper penny has a mass of 3.1 grams and a volume of 0.35 centimeter cubed. What is the density of copper? Okay, so they give us the mass, which is 3.1 grams, and they give us the volume, which is 0.35 centimeter cubed. Okay, so luckily for us, the equation for density, this requires mass and volume, and it is mass divided by volume. So our mass was 3.1 grams, and our volume is 0.35 centimeter cubed. So the density is 3.1 divided by 0.35, which is 8.86, and the units are in grams per centimeter cubed. Okay, so the junior tutor said the density of copper is 8.86 grams per centimeter cubed. Density is defined as mass per volume of a substance. Given the mass and volume of the copper penny, we can calculate for the density of copper. Yep, so 3.1, 0.35 is equal to 8.86. So this solution is correct. Okay, so question number 5. Where does lactic acid fermentation occur? Okay, so lactic acid fermentation. So this reaction occurs in the cytoplasm. And this takes place in the cytoplasm of both eukaryotic and prokaryotic cells. Okay, so I'll just briefly kind of show the reaction that takes place. So we have pyruvate, so 2 molecules of pyruvate, they get reduced. and to form 2 molecules of lactate. Okay, so the ketone here gets reduced to an alcohol, and the rest stays the same. And this is lactate. And during this reaction, we have NADH getting oxidized to NAD+. Okay, so once you start doing more biochemistry, you'll see more of these types of reactants and why NADH is used and why we have 2 molecules of pyruvate. So this is one of the steps in glycolysis. Okay, so the junior tutor said lactic acid fermentation is an anaerobic metabolic process to convert a 6-carbon sugar, for example glucose, to energy and lactate, a deprotonated form of lactic acid. Together with glycolysis, the fermentation in the cytoplasm, this fermentation is in the cytoplasm of the cell. One application of this process is the usage of bacteria in yogurt making. Yep, so this solution is correct. Okay, so question number 6. How many quarts are there per gallon? Okay, so we can just answer this pretty quickly. There are 4 quarts in 1 gallon. And the junior tutor said, a quart is equal to a quarter of a gallon, hence the name quart. Converting a gallon to quarts, we'll have 1 gallon times 1 quart over a quarter gallon is equal to 4 quarts. Note that for the conversion factor, the gallon is placed in the denominator because it is the unit to be cancelled, and the quart is placed in the numerator because it is the desired unit. Hence, there are 4 quarts per gallon. Yep, so this solution is correct. Okay, so question number 7. Calculate the mass of silver chloride formed and the concentration of silver ion remaining in solution when 10 grams of solid silver nitrate is added to 50 mils of 1 times 10 to the negative 2 mole per liter NaCl solution. Assume there is no volume change upon the addition of the solid. Okay, so this is a multi-step question. So first, we can write down the reaction equation that takes place. So we have silver nitrate, which is a solid, and it is reacted with sodium chloride solution. So I'm going to put aqueous, and this will form silver chloride, which is a solid, plus sodium nitrate. Okay, so now let's just make sure that everything is balanced. we have 1 silver on both sides, 1 chlorine on both sides, 1 sodium on both sides, and 1 nitrate ion on both sides as well. So everything happens in like a 1-to-1 ratio. Okay, so now I'm just going to write down everything that I know. In the case of the silver nitrate, we have a mass equal to 10 grams. And for our sodium chloride, they give us the volume, which is equal to 50 mils. But since its concentration is in moles per liter, I'm going to convert this to liters. So 0.05 liters. They also give us the concentration of the sodium chloride solution, which is 1.0 times 10 to the negative 2 moles per liter. Okay, so now that I have the two reactants, we want to find out which one is the limiting reagent. Okay, so if we look up the molar mass of silver nitrate, I'll just do that now. Then we can calculate the number of moles that reacts with the sodium chloride. Okay, so the molar mass is around 170 grams per mole. And if we were to calculate for the number of moles, for this solid, it is N is equal to mass over molar mass, which is 10 grams divided by 170 grams per mole. Let's look it up. So we get around 0.059 moles of silver nitrate. Okay, so now let's try to find the number of moles of the sodium chloride to find out which one is the limiting reagent. So to find the number of moles, it's just going to be the volume multiplied by the concentration. So the volume is 0.05 liters, concentration 1.0 times 10 to the negative 2 moles per liter. And then we end up with 0.0005 moles. Okay, so already we can see that our sodium chloride is our limiting reagent. So this means that the sodium chloride will run out first. And for our products, it would only form however moles of limiting reagent is there, because it will just run out and we won't be able to form any more product. So that's why it's important to try and figure out what our limiting reagent is. Okay, so let's look at the question, concentration of silver ion remaining in solution. So we need to find the concentration of silver in solution. I'm just going to write that here. So first, let's write down the moles of silver nitrate. So we started off with 0.059 moles. And since this is an excess, we'll have some of it left over. So since everything's at a 1-to-1 ratio, only 0.0005 moles reacted with the sodium chloride. So now let's just find the difference between the two. So this value subtract 0.1235. So you can see we still have a lot of our silver left over. So that's how many moles of silver nitrate there are. And now to calculate for concentration, the question said to assume there is no volume change upon the addition of the solid. So it'll just have the same volume of 0.05 liters. So it's just going to be 0.058 moles divided by 0.05 liters. And you should get around 1.17 moles per liter. Okay, so now let's see what the junior tutor said. Okay, so they wrote down the reaction: silver nitrate plus sodium chloride makes silver chloride plus sodium nitrate. Okay, so from the reaction, 1 mole of silver nitrate reacts with 1 mole of sodium chloride. So they found the moles of sodium chloride by doing concentration times volume to get 0.0005 moles. For the moles of silver nitrate, 10 grams divided by 170 grams per mole gave 0.06 moles. Therefore, sodium chloride is the limiting reagent. So the moles of silver chloride formed is 0.0005 moles. And they calculated the mass of silver chloride formed as well. Oh yeah, I didn't do that step. But yeah, to find the mass, it is just 0.0005 times the molar mass of silver chloride, which is 143 grams per mole. And you should end up with 0.0715 grams. So let me just quickly show that up here. So the reason why we use the limiting reagent moles is because this is the one that will run out. And let's just double check to make sure that this calculation is correct. So around 0.0715. Okay, so for the second part of the question, the concentration of silver plus left in solution, we have the starting moles, which was around 0.06, subtract however much reacted with the limiting reagent, and they got 0.0595 moles. Divided that by the volume to get around 1.19 moles per liter. Or, yeah. Maybe I'll just take note what the units should be. Okay, so the solution is correct. I'll just put moles per liter. And looks like they used decimeter cubed. Okay, so on to question number 8. How do you calculate the vapor pressure of a solution? So we can calculate the vapor pressure of a solution by using Raoult's law. So this can be shown using the expression the pressure of the solution is equal to P naught A. Okay, so I'll define all these terms in a bit. Okay, so when you have this P naught, or P with kind of like a degree symbol, this stands for the vapor pressure of your pure solvent. So this is when you have your solvent that doesn't have anything mixed in with it. And X is the mole fraction of the amount of dissolved solute present. Okay, so when you have the mole fraction of these two different compounds, A and B, it's also important to note that if you were to add these two values together, they should equal 1. So in a question, if you're given the mole fraction of one compound, you can quickly calculate the mole fraction of your other compound. Okay, so let's see what the junior tutor said. So they have two different scenarios where you can have a binary solution and an ideal solution. So for the vapor pressure of a binary solution, this is equal to the sum of partial pressures of components of the solution. So suppose that the solution has the components A and B. The vapor pressure of the binary solution is equal to the partial pressure of component A plus the partial pressure of component B. According to Raoult's law, the partial pressure of a component of an ideal solution is equal to the mole fraction of the component in solution multiplied by the vapor pressure of the component when it is pure liquid. Okay, so they kind of simplified what PA means. So XA times P star A, where XA and XB are mole fractions of A and B respectively, and PA star and PB star are vapor pressures of pure liquids of A and B respectively. So substituting the equation 2 and 3 into 1 gives us the vapor pressure of solution. So by knowing the vapor pressures of the pure liquids of the components and the mole fractions of the components, we can calculate the vapor pressure of solution using the above formula. If component B is non-volatile, then the vapor pressure of the solution P is equal to the mole fraction of A times the vapor pressure of pure A. Yep, so this solution is correct. Okay, so on to question number 9. What is the electron configuration for B? So vanadium. So when we want to find the electron configuration of an element at its ground state, we can go by the following steps. So the first step is to divide your periodic table into sections. Okay, so I can show what that looks like so that it's kind of easier to visualize. But most of the time you're given a periodic table during like an exam, so you want to make sure you know how to divide the periodic table into these sections. So for the S block, it is the first 2 rows, or columns, sorry, plus helium. So it is shown in light blue, and this is the S block. For the P block, it is this green kind of rectangle, and then the D block is this orange, so it is all the transition metals. And then lastly, the F block are the last 2 rows, which are the lactinides and the actinides. So part 2 is starting from hydrogen. You want to move left to right across the periodic table until you get to your desired atom. And then you want to write your row number and then your block letter. And then I'll also note when you get to your D block, you write your row number -1. And if you get to the F block, you write your row number -2. Okay, so this will make more sense once we start doing the example. So the example is looking for vanadium. So first, let's find it on the periodic table. And you can see that is right here, atomic number 23. Okay, so let's follow the steps Starting from hydrogen, if we were to move left to right across the periodic table, we write the row number and then the block letter. And then you also want to show how many electrons there are in each orbital as you go through it. So starting at hydrogen, it's 1s over to the helium, so you get 1s2. And then on to the next row, we have 2s2. And then moving across to the p block, we are still in row 2, 2p, and then if you were to count everything in that row, it'll be 2p6. And then down to the next row, we have 3s2, and then 3p6, and then 4s2. And then when we get to the D block, it becomes 3D, and then we want to count up to vanadium. So it is 1, 2, 3. So 3D3. So this is the long version of the electron configuration. So if we wanted to write this using the shorthand electron configuration, it's pretty simple. You just need to look at the noble gas that comes before vanadium. So in our case, it is argon. So we write argon in square brackets, and then we just continue on writing the remainder of the electron configuration, just doing the same way we've been doing, 4s2, 3d3. Okay, so let's see what the junior tutor said. The atomic number for vanadium is 23. The noble gas that precedes vanadium is argon. Hence, the electron configuration for vanadium is argon. So here, doesn't matter. You can write the 3d3 first, or s2. And this is because the 3d3 has a lower energy than the 4s2. And then they can show the orbital box diagram, so you can see here how the 4s has a filled orbital, and then for 3d3 you have 3 unpaired electrons. Yep, so this solution is correct. Okay, so on to question number 10. What is the formula for the heat of fusion? Okay, so first let's define the heat of fusion. This is the amount of heat needed to convert a solid to liquid at constant pressure. Okay, so when you want to have the formula for the heat of fusion, it can be denoted as delta HF is equal to Q over N. So Q is the amount of heat so this can be in either joules or kilojoules, and N is the number of moles. Okay, so let's see what the junior tutor said. The heat of fusion is the amount of heat required to change the phase of a solid at its melting point to liquid, and the heat released when a liquid changes to solid without a change in temperature. This can be calculated from the equation Q is equal to N times delta HF, where Q is the amount of heat, and N is the number of moles, and HF is the heat of fusion. Rearranging the equation for delta HF, we'll have delta HF is equal to Q over N. Yep, so this solution is correct. Okay, so on to question number 11. What are the differences between starch and cellulose? Okay, so I'll make a comparison graph. So I'll first write what these two have in common. They are both made up with glucose monomers. But in the case of their differences, for starches, the linkages are alpha, 1,4 linkages. And in the case of the cellulose, the linkages are beta 1,4. So typically, starches are more straight chained. And cellulose is more branched. Another difference is that starches are typically easier to break down. And cellulose is more difficult to break down. And if we were to try to compare their different functions, in the case of starch, we use this for an energy source. So energy source for humans. And cellulose is typically used to build plant cell walls. Okay, so these are the main differences between starch and cellulose. So even though they're both made up with glucose monomers, they have a lot of different differences. Okay, so the junior tutor said, starch and cellulose are both examples of carbohydrate polymers. That is, they are made up of repeating units of glucose molecules. Their main difference is that the starch occurs as a straight chain while cellulose is branched. I'd say the main difference is probably how the linkages, but I'll just write that down in a bit. Refer to the figure below to see the comparison. So apparently I can't do that, but let's look at picture just so that it's cool to see how they're different. So at the top is an example of a starch. So you can see the alpha 1,4 linkage. And if you look at the cellulose, the glucose linkage is a beta 1,4 linkage. Yeah, so that's one of the main differences. The junior tutor also said, moreover, cellulose builds the plant cell walls and cannot be used as an energy source by humans. Starch, on the other hand, metabolic enzymes fit to the geometry of the starch, hence can be used as an energy source. Okay, so the solution is correct. I'll also add some of my points as well. Okay, so I just kind of summed up what I said already. Starch contains alpha 1,4 linkages among the glucose monomers. It's easier to break down, straight changed, and an energy source for humans. Cellulose contains beta 1,4 linkages among glucose monomers, is more difficult to break down, contains branched chains, and is used to build plant cell walls. Okay, so those are all the questions for today's session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's session, then go ahead and give it a thumbs up and a comment. And don't forget to leave a comment, and you can share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.